Okay, in this next example, this is definitely a level 3 example. This example is actually going to require us to use a secondary equation, and I'll show you that in just a second. Water runs into a conical tank at a rate of 9 feet cubed per minute. The tank stands point down and has a height of 10 feet with a base radius of 5. How fast is the water level rising when the water is 6 feet deep? Alright, so let's get started in showing you a couple of things. First off, this amount here, this 9 feet cubed per minute, that's clearly a volume. So that's going to be dV dt, and it's running into it, so that means that it's increasing. So 9 feet cubed per minute. The tank stands point down, has a height of 10 feet, so that's important. The height of this tank from the top all the way to the bottom is 10 feet. Now, that's not going to change. That's going to be the same no matter what. So that's important information to know. And the base radius is basically the radius of the circular part of the cone right here, and that's your radius. That's going to be 5 feet. Now that's 5 feet always, because this tank isn't changing. But as we fill it with water, it wants to know how fast the water level is rising. So let's say we fill it with water. Okay. It wants to know the water level, which is from the tip of that cone all the way up. When that level is 6 feet deep, the question is, how fast is the water level rising? Okay, so a couple of things. The level of the water is in fact changing, so you must assign a variable to it. If you want to, we can just call it h. At the same time that that's happening, the stuff that you can see, it's circular. It sort of mimics that top circular part of the cone. That has a radius, and its radius is going to be r. And the reason we call it r is because as the water level increases, this radius gets wider and wider. Of course, the widest it could ever be is when this thing is completely full. When the tank is completely full, the radius would be 5 and the height would be 10. But between 0 to that, both the water level and the radius of that water, the top of the water, change as you increase the water level. What doesn't change is the actual size of the tank. Okay, so we have one radius, which is 5, that belongs to the tank, and the r belongs to the radius of the water part. 10 belongs to the height of the tank, but h is the water level. So the rate that we are looking for today is dH dt. That's the water level. How fast is the water level rising? Now, we're not given a whole lot of information about the radius at all. I didn't mention it, but this is gonna be important, because if we want to write an equation that relates volume and height, we're gonna have to Google or look up the volume of a cone. So let's go ahead and do that. Okay, so I did that and just kind of took a snapshot, and here's the volume of a cone, pi r squared h. What you're going to notice right away is that the volume, that's okay. The v is okay because we have dv dt. So when we take the derivative, we're going to be okay there. H is okay because that's going to generate dH dt, and that's what we're looking for. What's not okay is this r. You see, the radius, we don't have any information about the rate of change of radius, dr dt. And if we take the derivative of this, we're going to end up with the dr dt, and we don't actually have that information. So one of the things that we can do is that we can actually replace this r. But to do that, we have to find a way to write r in terms of h. And that's where that secondary equation is going to come into play. So what I want you to notice is, from the picture, we have a right triangle here formed by the h and the r. It's a right triangle. Well, we also have another right triangle formed by the height and the radius of the cone. And because we talked about similar triangles before, see how they They both have a 90-degree angle and they share an angle, so that means this third angle is the same. So these are similar triangles. If I draw those out again for you, the big triangle, big right triangle, would have, this would be 5, this would be 10, 90 degrees. The little triangle, which is the water, the one created with the water, would be R and H. Okay? And they're similar because they share those angles. So that means I can create a relationship here. So that means I can go maybe, I could go 5 over R equals 10 over H. It could be backwards too. You know, it could be R over 5 equals H over 10. But what I'm going to end up doing here is try to solve. This is a true relationship because of similar triangles. What I'm going to try to do now here is cross multiply and solve for H. And I'm going to get 5H equals 10R. And if I divide by 5, I get that H is going to equal 2R. So what that means for me is I can come back in this formula. Instead of writing it with an R and a H, I can replace R with 2R, which is what H is equal to in this particular problem. And now I will only have a V and an H to worry about, and I don't have to worry about that R giving me a R dt that I don't have. So I'm going to go ahead and do that. I'm going to rewrite that volume function as pi times radius squared, and instead of radius, I made a mistake. Let me go back. I don't need to solve for H, I'm sorry. I need to solve for R because that's the variable we're trying to replace, and I really don't want to start the video over, so scratch this guy. Instead we're going to solve for R. R is going to be 5 over 10 H, which of course is 1/2 H. Sorry about that. So again, we're trying to get rid of R because we have no information about dr dt. We want dh dt, so it's okay to keep H. We have dv dt, so it's okay to keep V. R is what's kind of out of place. So we use similar triangles to create a proportion, and then instead of solving for H, we actually need to solve for R because R is what needs to be replaced. So instead of R, I'm going to put a 1/2. Maybe I should erase that and make it nicer. I'm going to put a 1/2, and then it's going to be 1/2 H. That's squared, because remember the R was squared, and it's going to be times H over 3. So let's simplify this a little bit. It's going to be pi times 1/2 squared is 1/4. So we're going to end up with H squared over 4. That's the same as 1/4 times H squared times H over 3. And in the end, it becomes pi H to the 3rd power. This is 1, we add the powers, over 12. And that's our new volume formula. And the cool part about this is that it does not have R's. And remember, we don't want an R because we don't have information about the RDT. All of this work, guys, and we haven't even taken a derivative. This was just preparing the function so that it only had the variables that we needed. Okay? And there was no way to avoid that R because that's part of the volume formula, but we could create with similar triangles, we can create a relationship that allows us to replace it. At this point, I'm ready to take the derivative in terms of t. So that gives us dv dt, and remember, pi 12 is simply a it's a constant. So this is really going to be 3 over 12, which reduces to pi over 4 h squared times dh dt. Okay, now h was given at the beginning in the problem. It says how fast is the water level rising when the water is 6 feet deep, so that's going to be h, and dv dt was 9. So h is 6, dv dt is 9. Have to remember that. Alright, so dv dt is 9 equal to pi over 4. H was 6, so this is going to be 36 times dH dt. And dH dt is the water level, so that's what we've been trying to find this whole time. 36 divided by 4 is 9, so you can see how this is working out. 9 pi times dH dt. And dH dt then would equal 1 over pi. And the units for that, I don't recall. I think it was feet. Let's look up here real quick. It gave us the radius in feet per minute. Yeah, feet cubed per minute. So because, sorry, it gave the volume in feet cubed per minute. So this is going to be feet per minute. And that's it. So this problem is like it's a 3, but it involves you having to replace the variable because we're not given any information about the rate. Okay, so this is example number 2.